Okay, we are recording.
Oh, thank God. Yeah. Okay. Different recording stuff today. We're stuck in a. I'm stuck in a business trip overseas. In other words, meant for NUS. Makes it sound more glamorous than it really is. Okay. So let's begin. So today's topic, we're gonna talk about something called Big O, which is traditionally part of a different module, but I decided it was actually very relevant. You can ask my students in the other module. They all think that we should have taught it in this module. Actually, what do your students think, Nurul? Don't they prefer it taught in this module?
I don't know. I've never heard comments about Big O in. Yeah.
Hmm. Interesting. I thought they would actually say something, but I guess not. Okay, so let's begin. So before I even talk about the formal definition, let's talk about why you need this stuff, right? Because for once, I think the motivation of the application kind of is a bit more important, or at least like if not, it wouldn't make sense why we're doing this. So imagine you write some Python code. I guess I don't know something like for I in range length of your arrays, maybe something like this, and then maybe you just want to add to like some sum, right? So it's like you want to say like total equals to array like the ith item of the array. So maybe something like this. Uh, you might want to write some code like this, right? So you can imagine how the number of iterations that you're going to make in your code, right? So like this, oh wait, sorry, I said array total, but I meant to say array plus equal, right? So array plus equal total. Oh, sorry. The total plus equal array I, right? So you can imagine how the number of iterations that you're going to make here, right, is actually the number of times you're going to run this line is actually proportional to the number of elements in the array, right? So you can imagine how if you have an array of, let's say, so the array size, right? So you could have an array of maybe like size 1, size 2, size 3, so on and so forth, and you can imagine how the number of iterations that you're going to make is basically proportional to this, right? In fact, like in this case, like with the size 1 array, you're just going to make one iteration, two iterations, three iterations, 4 and 5, and so on and so forth, right? So 4 and 5, right? And basically, you might want to argue about the running time or the time taken for your program to run. Okay, so it might be the case that if you use a different programming language, right? The exact time taken might be different. So you can imagine how if I had another time taken sort of like measurement. Okay, and in fact, like that's the whole point of this graph, right? So if I have a whole time taken curve, right, the amount of time it takes for the Python code might not actually be the same as the amount of time it takes for the Java code, which might not be the same as the amount of time it takes for the C++ code. In fact, normally people would argue that the C++ code actually would run the fastest actually. But the trend, which is the important part that we want to capture, right? The trend is the same. In this example, right, for this code, we want to say that all of these are linear. In other words, they're sort of linearly related or they are proportional to the array size, right? So we don't know what the exact curve is. It's not really a curve, it's a line, but we don't know what the exact curve is. But we know it's proportional to the array size. Okay, so in some sense, we want a way to capture the, like a way to communicate and say that basically, um, that this running time is just some linear trend of the array size, right? And this is only specific to this kind of code actually, because different programs give you different trends. That's kind of the idea. But in computer science, this is something that we really care about a lot. We don't really care about the exact running time. We don't care about the exact curve. We care more about the behavior or like the long-term running behavior of the code. Okay, so to show you what I mean, I have a slightly more complex example here because you might be thinking to yourself, Eldon, everything has to be proportional to the array size, right? So I'm going to give you two examples here. I have sort of like 14 lines of code here, and they are basically, both of these functions are trying to accomplish the same goal. They're basically trying to sort your array. Okay, and if I know it's a lot of code, you can trace it on your own time. We're not really going to do that here. I'm just going to give you a rough idea. But basically for this code, the idea is going to be that it's going to first fix an index 1, and it's going to try to iterate to the end of the array. So index 1 is going to start at the very beginning, and at the next iteration, oh, it's same color, huh? Yeah, at the next iteration, it's going to move to the next point of the array, then the next point of the array, then the next point of the array, and the next point of the array, right? So that's what index 1 is doing. Index 1 is heading forwards. And the intuition is that for every value of index 1 that we fix, index 2 is going to iterate backwards. And it's basically going to try to sort of do this swapping thing. So the way that it works is that it will check whether 3 is smaller than 7, which it is, so it will do a swap. And after that, so 3 will move to this position and 7 will be here, right? And then 3 will check against 5 as well. And if 3 happens to be smaller than 5, then we'll do a swap again. So 3 will sit here and 5 will sit here and 7 will sit here, right? So this line of code basically does that. And the idea is that if we just ran this algorithm, right, from start to finish. Wait, hold on. I looked at the wrong one. This one, right? So if we look at this algorithm from start to finish, okay, then basically what it's doing is pretty much just iterating, moving one index forward and iterating for every setting of this index. It's just going to iterate backwards on the other one, and that's how it tries to sort. Don't ask us why it sorts. Actually, you can figure it out. But we're not focused on why it's sorting today. We're just focused on the running time. Does that make sense?
Yeah.
Okay. Stop
It
me from
takes a while
speaking.
to read the code, but okay.
Yeah. It does take a while to read the code, right? But basically, the idea, the intent here is we just think of it this way. This is iterating backwards, and if the item is smaller than the item in front of it, then we do a swap. That's what this swapping thing does, right? I don't
Mm.
know if you guys know that you can write your Python code like this. You can write commas here to swap, but now you know. Okay, well, there is a different way to there's the there are many possible ways to actually sort your arrays. Okay, so for example, instead of the first function, right, we have another function here. Again, it's going to move index one forward, so index one is going to go forward. Okay, and this code here instead is going to start from index one to the end of the array, and it's going to look for the minimum element. That's the idea. And when it finds the minimum element, it's also going to do a swap. Okay, so in this code, for example, you're going to start from this iteration and you're just going to move forward. And the idea here is that starting from this position onwards, you're going to try to find the minimum in this portion of the subarray. And once you find the minimum, let's say it's this one, then what you're going to do is to perform a swap. So 8 and 9 will swap. So 9 will sit here and 8 will sit here. And you will put the smallest element in this position. Then you rinse and repeat for all possible values of index. Okay, so this code also actually does sorting. You can imagine how the way that we've iterated on this program, like this I guess we call, what do we call it? I call it sorter one, right? So on sorter one, right, the way that I've iterated is different from the way that we've iterated in sorter two, right? But at the end of the day, both of these programs actually sort the array. Like they're both sorting functions actually. So they both sort the array. Okay, but the exact way that they've done it is different, and you can imagine how the amount of work that we would have done in this portion of the code, okay, might not actually be the same as the amount of work that's being done in this portion of the code, if that makes sense, right? Because it's very hard to say that we can look at lines 4 through 6 and say that, oh, the amount of time that it's going to take is going to be more than the amount of time it takes from lines 10 to 14. Something like that is actually very hard to quantify. And if you run your experiments, like you might be surprised like which one is actually faster, which one's actually slower. But the point is that we don't really care about what the exact time taken is for these two methods. What we actually, oh sorry, functions. I don't know why I said methods, but functions. Um, so the point is that if I were to try to plot these two on a graph, right, we might see something like these two lines where they kind of curve upwards. Okay. Again, one of them, let's say, is for like the running time taken for sorter one, and one of them is the running time taken for sorter two, right? So the point is that both of these are actually very similar looking curves, or at least to computer scientists, we would be very happy to say that they behave similarly, right? So we kind of don't really care about the exact time taken, even though I'm plotting a curve for you. What we care, again, like I mentioned, is more about the trend. Okay, so if you actually try to count the number of iterations that we do in this code, okay, you can imagine how it's going to be very similar to the number of iterations that we're going to do in this code. And the way to reason about that, if we count it carefully, okay, like for example, if you take sorter one, the amount of times that the first iterate the for index one, because we're iterating backwards, okay, the idea is going to be that when index one is one, okay, the inner portion of this while loop is actually only going to make one iteration. It's actually only going to make one iteration. Okay, so in the innermost iteration is going to be one, right? And when index two is two, sorry, if the index one is two, okay, then the innermost thing is actually only going to make two iterations. When index one is three, then the innermost thing is also going to make 3 iterations, and you can imagine where this is going, right? So eventually at some point when index 1 is n minus 1, that's the highest possible value, then at most we're going to make n minus 1 iterations. So in total, the amount of iterations that we make happens to actually be 1 plus 2 plus 3, so on and so forth until n minus 1. And if you sum this up, you should get, help me out here. What would you do?
Uh, the thing is like n times n minus 1 over 2.
Are you
Yeah,
sure? Oh, okay, you said n minus 1, damn it. I
yeah.
was going to catch you.
I got it.
'Cause I thought you would say n times n plus 1, which is wrong. Yeah, so you get n times n minus 1 over 2. Right, so these are the
We
number of
proved this by
iterations.
induction last week.
Oh yeah, we did.
Yeah, we
Uh,
did.
we did. Right. So you would make n times n plus 1 iterations, and you can imagine how the running time here is again proportional to your number of so your running time is proportional to your number of iterations. I mean, of course, the more iterations you take, the longer it takes to run something, right? Um, and likewise, for this code instead, right, the way that it works is that at the very first at the very first index, okay, I've scribbled a lot over the screen, but let me remove this, right? So you can imagine how like at the very beginning when index 1 is here, we have to iterate across the entire array. So that's all n elements, right? And then when index 1 eventually increments and points to this index, then you have to iterate across n minus 1 elements, then n minus 2 elements, then n minus 3 elements, then n minus 4 elements, so on and so forth. Right? So basically the number of iterations is going to look something like this. It's going to be like n elements, followed by n minus 1 elements, followed by n minus 2 elements, followed by n minus 3 elements, until let's say 2, something like 2. Okay, so the amount of iterations here, okay, would basically be, oh, actually, yeah, let me ask you, how would you resolve this now? This looks like a curveball, right?
Okay. Wait, n plus 2 times how many terms are there even?
So there's it's
And
basically two, three, like if I count backwards, right? It's two,
yeah.
four, five until n, right?
Mm-hmm.
So how would you resolve this? We probably want a closed form solution for this.
Right. I mean, you just apply the same formula as the top, right? So it's n plus 2 times
N
n
plus
minus 1?
2
Oh, bruh. I'm
n.
messing this up.
Yes, you are. Hehe. Okay, let me show you how I would do it. Let me show you how I would do it. So what happens if I put a plus 1 here?
Okay, sure. This is way easier then. It's just n plus 1 times n. Yeah. N times n plus 1 over 2.
Over 2,
Yeah.
and we had the plus 1, right? Just
Yeah,
now.
so just minus
So
1.
plus 1, right? So you minus 1, right?
Nice.
So this entire thing resolves to this, and you just take the plus 1 and the minus 1, you keep it over, right?
Hmm.
Okay. So we have two different methods. We have two different functions, right? One of them says that we do this many iterations. One of them that says that we do this many iterations. Okay, so at first you might wanna potentially like look at these two curves and say like, oh, like one curve is maybe like better than the other one, right? Because these are our ways to predict running time, right? Now we're saying that like for example, let's just say for example maybe n equals to 5, right? Then maybe we would want to say that this code here, this upper code here would make, let's see, 5 times 4 divided by 2, which is what, 10 iterations, right? And maybe you want to say that this code here, which is what, 5 times 6 divided by 2 minus 1, which is 14. Maybe you want to say that the upper code is faster because it makes fewer iterations, right? But it actually doesn't quite work that way, because we are only guaranteed that it's proportional to the number of iterations. We don't actually know what the exact relationship is. In other words, we don't know what the constant factor is, right? Because again, even though we can count the number of iterations, we don't really know what the amount of time taken for this, like this iteration is, right? Like how many milliseconds does this, like these iterations take compared to these? Well, it's kind of like comparing apples to oranges here. You can't really tell. You can't really tell the difference. I mean, sorry, you can't really tell, what the exact difference in running time is. Okay, so in some sense, as computer scientists, generally we don't actually bother We don't actually care about the exact number of iterations. So what we're actually going to do is to try to find a way to just say that basically, roughly speaking, these two have the same similar behavior. Okay, we basically want to say that these two have a quadratic trend, like a quadratic behavior, right? So if you think about the n times n plus 1, sorry, n plus 1 divided by 2 minus 1, right? This actually roughly looks quadratic. So if I were to expand this out, okay, we would actually get n squared over 2 plus, let's see, n over 2 minus 1, okay? Or the other one that we have, which was n times n minus 1 over 2, right? This is basically n squared over 2 minus n over 2, right? They both basically have this n squared term in it, right? So we basically want to say that they have a quadratic trend. You know, we're basically going to start trying to ignore these lower order terms because they actually, in the grand scheme of things, won't matter too much. So what do I mean by this, right? So let's just say that I have two programs for whatever reason, okay? And let's just say that for the blue one that I have here, we know that the trend is, let's say, something quadratic, maybe like 5n squared, let's just say, hypothetically, as an example. Okay, and let's just say that I have another program here that tries to solve the same problem, but but it's a green curve and maybe it looks something like, I don't know, 1,000 log n, maybe something like this. Okay, so we have two curves here. Okay, and the idea is going to be that we don't actually really care about the constants. We don't really care about these constants because I'm gonna try to argue that no matter what these constants are, the intuition is that because this function is smaller, in some sense, I'm going to put smaller in quotes here because we haven't really like mathematically defined this yet. But let's just say because this function is smaller, okay, the idea is going to be that we want to use this as a way to say that as n tends to infinity, okay, this green this green curve, I'm going to be very vague here, but this green curve will be overtaken by the blue curve. That's the idea. Okay, so why do we care about talking about this for computer science? Well, the idea is that when you want to eventually move on from this course and talk about algorithms or talk about efficient programs, okay, we basically want to find programs that behave efficient, right? So the idea is that we want to find algorithms that for large problem sizes, which happens to be on the right side of this curve, right? Anything as n so as n tends to infinity, that's what we mean by as problem sizes get bigger, right? We want programs that use less and less time, right? That's kind of the idea. So you can think about how the green curve, even though it starts off being, even though it starts off taking more time than the blue program, let's say. So there's a green program and a blue program, right? The intuition here is that even though at the very beginning, maybe the green program takes, even more, let's say, computer cycles or time to compute whatever it's supposed to compute. The intuition here is that as the problem size gets bigger, right, the amount of time that it takes relative to the blue program is actually a lot less. And you'll actually see a lot of programs that kind of look like this, where maybe at the very beginning, the amount of work done is actually quite a lot, but as n tends to infinity, it turns out to actually be very efficient. And what we really care about is just really its long-term behavior, or its large input behavior. So what we care about is as n tends to infinity, we kind of want to have programs where their running time function, right, will be overtaken by other ones, because that's what we would call being efficient. That's okay. Super vague. I know. We'll. The next thing is pretty much a definition already, but so far does this all kind of make sense?
Yeah, the intuition, but yeah.
Yeah. Were you gonna say but too vague?
No, no, no. I am in fact gonna prep the students that yeah, we're going into rigorous math now.
Yeah, we're going to rigorous math now. So okay. So let's move on to the definition of big O, which happens to be, well, the formal thing. You might see that the scribbles on the screen already. Totally not because we made a mistake and had to cut out the previous portion. No, it was always just here. The hard cut meant nothing. But let's talk about definition of big O. So let's think about fn as a function. So again, your function here, like for example, right, you can take as an example, if we need one, so something like, n squared over 2 minus n over 2, this is an example of a function, right? So let fn be such a function on the natural numbers, so we only really care about natural numbers. Okay, then we're gonna show you a set called O of fn. So in other words, the definition of this set actually depends on your function fn. But in general, right, what functions does this set contain? So this is, I'm going to tell you right now, this is a set of functions. Okay, this is a set of functions, and the way that this works, okay, is that we're going to hold functions gn. So in other words, gn is going to be in the set O of fn. Okay, if it basically fulfills the following condition, if it fulfills that there exists an n0 in n and exists a c in r plus. Okay, we'll explain what this is in a bit. Okay, but then we say for all n in n such that I know I wrote this here, but I'm going to show you a different way of writing this. I'm going to say that n greater than or equals to n0 implies that gn is smaller than or equals to, let me scroll, c times f n. Okay, so let's read this back. What is this trying to do? What's this trying to say? It's basically trying to say, okay, that there exists, here's the intuition, that there exists a starting point. This n0 here is a starting point. There exists a starting point, and there exists a multiplier. So think of this as your constant factor. Okay, such that for all n that is, well, I mean, okay, I'm going to combine these two parts together because that's what it is, So when you we're basically saying for all n that is greater than n0, okay, we must have that gn is smaller than the constant factor that we mentioned just now multiplied by fn. Okay, so as an example, let me run through an example with you guys. So if we consider a set like, let's say, O(n squared. Okay, so again, remember, this is a set of functions. Okay, and this set basically holds any function, any other function, we're going to call them gn, right? So that this promise applies. In other words, past a certain point, gn must be less than c times fn for some positive constant multiplier c. Okay, so let's go through a few examples. Let's say, what's an easy one? Or maybe not easy, but straightforward one. Okay, what about this? Maybe unintuitive. I don't know. Let's try to work this out. Do we think that 5n squared is in O of n squared? What do we think?
We have to work through the definition, I guess.
Okay. So to work through the definition, right, we need to do a few things. Okay, we need to find a starting point.
So this is your n0.
Exactly. So we need to find a starting point n0. We also need to find a constant multiplier, right?
Mm-hmm.
C. Okay. And once these two need to fulfill a condition, and that condition is that for all n greater than or equals to n0, using a shorthand here, okay, what we must have is that 5n squared, okay, has to be less than or equals to c times n squared. Okay, so I guess maybe writing it out makes it a little bit obvious what we need.
Yeah, so let's just try setting like c to 5, and then n0 can just be 0, I guess.
0, right?
Yeah.
Okay, so let's work with that, right? So let's see. We don't actually need to prove this at this point, I suppose, but basically let's think of it this way: for all n greater than 0, right? I think it stands to reason, right? 5n squared is actually less than or equals to, well,
It's equals to.
n squared. Yeah, because it's equals to 5n squared, right? So, it's okay. Easy example, makes sense, right? So we'd be happy to say that this is true. Make sense?
Mm-hmm.
Okay, so let's keep going. So let's try another one. Um, hmm. What about something like um, let's say 1,001 n.
Hmm. So back back to the definition, I guess.
Uh-huh.
Uh let's see.
So you gotta pick a starting point and you gotta pick
Yeah.
a constant multiple.
I mean the easiest way is you just match the constant multiple c with the, coefficient of n. So we try setting c to be like 1001.
1,001.
Yeah.
Okay.
And then n0 can be 0.
Yeah, actually, that probably
Yeah.
still works too, right?
Yeah.
Because if let's consider all n greater
Okay.
than or equal to 0, right? Yeah, most of the times, right? By the way, this does the heavy lifting for you actually.
Right.
Yeah. So for example, let's say, for all n greater than or equal to 0, I think it's pretty fair to say, right? So, 1,001 n, okay, is probably less than or equals to 1,001 n squared, right? And this is the c that we chose actually. This is the c that we chose. Right? So, yeah, that pretty much actually works. I'm trying to think of an example where you're forced to use the n.
And you just
You,
have to plus minus a constant, I guess.
I
So like
think
1000 n plus
yeah. So I'm thinking we do this. We do n squared minus 1,000 n, or let's say
minus. Yeah, okay.
yeah. So I think this would be an example where you're forced to use n0,
Right. So
because I think the intuition is this, right? So if I put n here and this is fn, then I think like the quadratic curve probably looks like this, but then the green curve, this one here with the minus 10n, probably looks like uh I actually don't, maybe like I don't know, like this or something. But they're both quadratic, right? The point is that they're actually both quadratic.
mhm,
A quadratic thread, right? This still has a quadratic thread,
right.
right? We need to be able to capture this somehow. Oh, actually, it wouldn't look like this. It would look like that was incorrect. This is the wrong graph. It would look like this, probably. But it's still quadratic thread. Yeah, yeah. Sorry, yeah. Go on. Yeah. So
Yep, okay, so we'll work with this example, right? N squared
yes,
minus 10n.
yes.
Intuitively, I can't think of it. Let's see.
I also probably need to think about like what values of n0 and c to set actually. I would Okay,
Wait,
gut
wait.
feeling.
Need to do
Alright,
some math here.
you need to do some math
So,
here. Okay, how would you do it? I want to see you do it.
right, so
We can
you
work it
did this.
backward.
You did this in the 2040S class, I guess. You just need to show that this is less than some
Uh huh.
c times gn. Right, okay, no
Okay,
worries. You just say this is less
right.
than uh
Uh
wait, is
huh.
this true? This is not true, right? Because it's the
Wait, but why are you showing that it's less than n squared minus 10 n squared? Oh, I see the trick
yeah,
that
I'm
you're
just
doing.
trying to
No,
make all the
but you
n's
can't you
into
can't do that.
n
You can't
squared.
do that. You can't do that because okay, I'm guessing what you wanted to do is convert this into an n squared, and then what you want to do is you want to do 1 minus 10 n squared,
Yeah,
right?
so then you get the constant out.
Yeah,
But
but the problem is that minus 9 here, you can't say this because our definition requires that C be positive, right?
yes,
Yes, yes, yes.
yes. Okay,
So nice
so
try. Try. That
back
doesn't
to
work.
the drawing board again. Yeah, but you have to somehow argue that you have to get rid of this part here.
Mm-hmm.
Thinking.
I would say like let's start with what we want, right? So
Mm-hmm.
let's just do this and let's just dump a
C.
C. Yeah.
Right, okay, then you just solve for the C.
Yeah.
Uh,
And in solving for the C, you might need n to be beyond some value, right?
yeah,
Oh, I thought of an easier way.
okay.
I thought of an easier way. Okay, as in I think it's the same thing. I think it's the same thing. Let's set C equals to 1,
Okay.
right? So for this to be true, this is true if and only if
Okay, okay.
if and only if minus
You can
10n
solve for
is
n
less
already,
than-
okay.
yeah, you can solve for n, right? So
Yeah.
now n just has to be, in other words, okay, if I multiply on both sides, it basically just means that n has to be greater than or equals to 0. 10n has to be greater than or equals to 0, which is true if and only if um let's see, n is greater than or equals to 0. In fact, yeah, that would work. That would work, right? So let's see, right? Let's think about this. Let's consider all n non-negative, right? So any n is greater than 0. Well, n squared minus 10n actually, we were thinking in circles, but basically this is pretty much just less than or equals to n squared, right?
Is
Because it's
it? Hmm.
the negative term, so you can just throw it away, right?
Right.
Right? Does that make sense? So let's try one more.
Yeah, okay, okay. Crap, we need to think of good examples.
Yeah. So
I'm just
let's
thinking of
do
just plotting the curves.
let's
Okay.
do this is what happens when it's unscripted. Let's do n squared minus 10n plus 100. Okay, now probably not so easy, right? So now we need to find again a c and an n0. Okay, so probably let's try from where you what you wanted to do, right? So let's try n
Mhm.
minus 10n plus 100. We want this for some reason, like somehow, not say for some reason, but somehow be less than or equals to c times n squared,
Mhm.
right? So I guess we do the equating thing, and we might not know the value of c that we want, right? So I guess if we try to move the like terms together, somehow, actually, I want to try something. So let's set this to
Mhm.
1,
Mhm.
right? So let's just hard code this to 1. Okay. So now we probably have that minus 10n plus 100 has to be less than 0. Cancel both sides, right?
Mhm.
So now 100 less than or equals to 10n, or in other words, n is greater than or equals to 10.
Yeah. It should
Right.
work, right?
I
The
think it
math
should work.
checks
So
out.
the math does check out. So so if you did this, right, then this feels a lot like high school math, but now you can say for all n greater than or equals to n0, or okay, well, I say n0, but actually what we mean is for all n greater than or equals to 10, okay, we're guaranteed that n squared minus 10n, sorry, minus 10n plus 100, okay, is less than or equals to n squared, pretty much. Okay, so this is kind of how you use big O. Should we give another example? I guess we should give another example, right?
Yeah.
Um, okay, maybe something like n cube.
Mhm.
This is too bright.
Oh, right. Yeah, you need one of the negative examples. Okay.
Yeah, for sure. We need a negative example, right? So maybe something like n cubed over 10 to the power of 6. Okay, so question is this in O of n squared? Okay, so let's see,
Yeah.
right? So remember, if we well, we already said it's a negative example, right? So we obviously know the answer is no. We obviously know the answer is no. So what we need to show is the negation of the statement, which actually happens to be for all n0 in n, for all c in r plus, exists an n such exists a natural number n. So exists an n in n such that how do I write this, huh? N is greater than n0, and uh n cubed over 10 to the power of 6 is bigger than c times n squared. That's the idea, right? So this is what happens if we don't believe that, this function happens to be in this set. Okay, so let's try, right? So we want to be able to argue that uh okay, essentially, I know I wrote a lot of abstract stuff, but I forgot to give you the intuition. Here's the intuition. The idea is that if gn happens to really be in O of fn, okay, then the intuition here is that gn as a curve, okay, is basically at most, at most, should I use green? I don't know if I should use green. Let me use blue. Is at eventually at some point, okay, so let's call this point n0. This point n0. So from this point onwards, n0 onwards, okay, this this blue function here is some constant multiplied by fn. So gn is at most some constant multiplied by fn from n0 onwards. That's really what this is saying. Okay, so if we don't believe that n cubed over 10 to the power of 6 is O of n squared, well, then the idea is that this overtaking will never happen, no matter what constant we pick. So no matter the c that we pick, okay, no matter the c that we pick, no matter the constant that we pick, the starting point that we pick, no matter what happens, this overtaking will never happen. Okay, so the easiest way to show this actually happens to be the following. Here's how we're gonna do it. Okay, let's suppose for the sake of contradiction that n cubed divided by 10 to the power of 6 is less than or equals to c times n squared. Okay, so we're going to suppose that there does exist a starting point n0. Okay, we're going to suppose that there does exist a constant c plus from r plus, right, such that for all values n greater than n0 onwards, this will happen. Okay, well, for this to happen, let's see what this must mean. Okay, if I divide n squared from both sides, it must mean that my constant c has to be at least n over 10 to the power of 6. Okay, or in other words, I'm going to basically argue that this must mean, okay, that n has to be at most c times 10 to the power of 6. Okay, but this actually has to be a contradiction, because we're basically saying that this is true only when n is less than or equals to c times 10 to the power of 6. Okay, when in actuality, we actually need this thing to hold for all n greater than or equals to n0. Right, so it actually means no matter the constant value that we pick, we're always going to run into trouble. Sorry, yeah, you were saying?
No, I'm just trying to find the contradiction. Yeah, okay.
Right, yeah. See, this
Mm.
is what happens when you start writing proofs in a loose way, right? It starts looking a little weird, but
Mm.
yeah, right. So that's kind of the idea of how big O works. Okay, and again, big picture, why do we care about big O? Okay, so here's kind of the idea, right? So let's just say that I have a lot of programs, and each of these running times here, on the y-axis is my running time, and on the x-axis is my input size. Okay, and over here I have all of these graphs and all of these plots and all of these curves, right? You can imagine how maybe this is like some function like 10n. Maybe this is, I mean, I'm not really sure, right? I forgot what constants I use, but maybe this is some function like 5n, and oh sorry, that can't be 5n. This has to be something steeper. Maybe something like 20n, right? And maybe this is something like, I don't really know, but maybe like let's see, it does look kind of steep, but not really. Maybe like 25 and minus I don't know, 15, something, right? Meanwhile, there's this red curve here that at the starting point, right, seems to be more efficient than the rest, right? Because it seems to take the least amount of time. In fact, you can see how it's actually really taking the least amount of time, right? But as the input size grows larger, so as n tends to infinity, as the input size gets larger, it actually really does take longer, and eventually does overtake the green function, the purple function, and actually even eventually the blue function, right? So in some sense, this red function, right, which actually was probably a quadratic function, so it's like some O n squared function, okay, um, eventually will be less efficient in all of these linear curves. Okay, so in some sense, we as computer scientists, we want to look at these curves and we want to basically say that this red line is not good. We don't like the red line. Even though it seems really fast at the beginning, that's not what we care about. What we care about is for large values of n, or as n tends to infinity, right? So this red curve, what we basically say is an O n squared curve. In other words, it has a quadratic running time. Okay, that's basically the term that we use. You're gonna see this again in if if my colleague does his job right, you'll see this again in 2001. Yeah. If you quote me, I guess maybe there will be some workspace conflicts, but uh,
Yeah.
you would almost definitely see this. Like basically, they're gonna talk about the running time of algorithms, and that's basically the mathematical definition of the running time that we care about, right? So again, the intuition is as n tends to infinity, the kind of trend that the function is. That's what we care about. Okay. And we don't care about constants. So we don't really care about running time constants. Where was the part where I said that we don't care about constants? It's somewhere. It's gone. It's here. It's here. Right. So we don't care about constants. We don't really care about constants. And as long as it's from some starting point onwards, this is completely fine. Right. That's what Big O says, basically. Okay, now big O is not really a silly theory thing that only mathematicians and theoretical people use. If you ever have to Google any algorithms in your lifetime, which I suppose you should and will, don't just use ChatGPT, please. I highly discourage that. But you might notice on your wiki pages, if you Google anything like, let's say, what is this one? Let me try to think. This one says best case performance O1 solves, ON comparisons, worst case complexity. Oh, but it says worst case ON squared solves. So is this bubble sort or is this selection sort? This looks like selection sort. I'm gonna say this is selection sort, right? So if you look up the wiki for selection sort, okay, if memory serves me right, you're actually going to you're going to see this thing. In fact, if you Google any algorithm that you're going to study, you're going to see this thing, okay, and you're going to see these funny little symbols there. Okay, so what do these mean, right? The idea how you should read this back, okay, is intuitively speaking, okay, it's at most some constant multiple of n squared after some n greater than or equals to n0. That's kind of the intuition. That's how most computer scientists look at it and see it, unless somehow Yorong doesn't see it that way, I suppose.
Oh no, I do see it that way. I'm just thinking, is it the correct sort? Uh, Selection sort in the best case assorted array, you still have to you'll find the minimum, right? So then you'll still be n square comparisons, I
You're
feel.
right, you're right, you're right, you're
So
right.
it's
I,
either
I,
like
I
bubble or insertion.
insertion
Mm.
sort. I do think I do strongly think this is insertion sort now. Yes, you're right. Don't let the 2040s kids see this. They'll probably put me
Yeah,
in the
you
yeah,
don't teach you don't teach their
we don't
structures
tell the
anymore.
2040 students. So it's a few days before their midterm, and I'm here in a foreign country recording a lecture for you guys.
Yeah.
But yes, average case compare. Okay, I should have seen this and realized. Yeah, average case anyway, I'm yeah, select insertion sort. I don't know why I said selection sort. Yeah, yeah. Anyway, that's what this whole thing is, right? So O n squared here means it's some constant multiplied by n squared. So it could be n times n minus one over two. It could be like, I don't know. It could be like n times n plus one, over two plus five. I don't know, right? We just know that it has a the running time has a quadratic trend with respect to the number of array elements, right? So if you see an ON, it means that it's a linear time, it's a linear relationship. If it's ON squared, it's a quadratic relationship. You can imagine how if it's a ON cube, right? Then this somehow has a cubic relationship, so on and so forth. That's the idea, right? I don't even know what the names are for like n to the power of 4, n to the power of 5, or like n to the power of like 1.5 and all these things. This is yeah, but but this is what we use, right? So this is big O. So following up from big O, we actually also have big omega, okay, which is very similar. So there is still there exists a starting point, there exists a constant multiple, such that for all n greater than or equals to that constant multiple. But this time around, instead of less than or equals to, it's greater than or equals to. So here's the intuition, right? If Gn is at most C times Fn, right, past some n, so past some n0 onwards, then we say Gn is in O of Fn, right? So Gn, in some sense, is quote unquote at most Fn, so it is in the set of OFN. Okay, omega is the counterpart, right? So this one is when Gn is at least C times Fn. So the intuition, right? So for this to say that Gn is in omega of Fn, so this is pronounced or read omega, right? The intuition here is that now we're saying Gn is quote unquote at least Fn. Well, C times Fn. That's what omega says, right? So in some sense, you can have Gn maybe as a function look like this, whatever that function is. I'm actually very impressed. That looked very nice. Let me use a
Yeah, it
different color.
does.
Right? It does, right?
Yeah.
Damn. Screenshot of this. I should take a screenshot of this and use it in my slides for algorithms next year. And, okay, right? So maybe this is my function Gn. Okay, and from below, I we don't really care what Fn looks like. It doesn't really matter. But if at some point it starts, like lower bounding Gn. So in other words, let's say, I suppose based on my example, like from this point onwards, right? So this is my n0 onwards. If I can find a C multiplied by Fn, right, then we would say Gn is in omega of Fn. Okay. On the other hand, if we could, on the other hand, find some function also, I mean, I'm going to call it Fn, I guess, right? Where, it doesn't really matter what happens at the beginning, but from that n0 onwards, right, Gn is at most C of, oh, sorry, I'm botching this up. Gn is at most C of Fn, right? So if it's bounded by from above, okay, then this we would say Gn is in O of Fn. So we now have a way to say less than or equals to, and we now have a way to say greater than or equals to, right? In some sense. So this would be O of Fn. And okay, I should put quotation marks because it's not really correct, right? Quotation marks. And if Gn on the other hand is greater than or equals to Fn, we would say that Gn is omega of Fn. Does that make sense?
Mm-hmm.
Okay, so the last thing we talk about is theta, which I know third definition and all, but it's pretty simple. Okay, so we're going to say that Gn is in theta. This is theta of Fn. Okay, if and only if Gn is in O of Fn and Gn is in omega of Fn. Okay, so in other words, think of it this way: Gn is some function, okay, and it is sandwiched by both well, the intuition is that these are the same function actually. It's just that it's like C1 times Fn and C2 times the very same function Fn. C2 times the very same function Fn. So this is Gn. So intuitively here, Gn is being sandwiched by both of these functions. Yeah, that's what it means to be in theta of Fn. Okay, so as an example, something like, let's say 5n squared is actually in, it's probably not a very instructive example, but 5n squared is actually in theta of n squared. Okay, so here's the intuition. Well, 5n squared is kind of, roughly speaking, let me use green. But 5n squared is, roughly speaking, I guess, as a very extreme example, at most 10n squared, right? We could totally say this. Okay. 5n squared is also, okay, you know what? I don't like this example. Yeah, like I pulled it out and I'm very unhappy with this example. I'm gonna use a better one. 5n, let's use green.
We need a
5
like breakpoint or something.
breakpoint, as in like for an n0 or what?
Not as in for your editing.
Oh, no, it's fine, it's fine. We'll
Okay.
keep going for this one. It's a very innocent thing. It's fine. Yeah.
Okay.
5n squared minus 100n. Let's say plus 10 to the power of 6, I guess, right? Something like this, right? This function is actually in theta of n squared. Okay, so the intuition is kind of like this. um I need to show two things, right? I need to show it's in O of n squared. So I need to show somehow this function is in O of n squared. So let's do that. So 5n squared minus 100n plus 10 to the power of 6 is actually less than or equals to pretty much 5n squared plus 100n squared. I'm just turning this minus into a plus, and I'm turning this into n squared plus 10 to the power of 6n squared, which actually is equals to okay, I shot myself in the foot here, but 1, 2, 3, 1100 n squared, right? Then this is for all n greater than or equals to 0. So we're fine, right?
You
So
have one extra zero.
do I?
10 to the power of 6 only has 6 zeros, right?
Oh, okay, okay, fine. Then less than equals to.
Oh, okay, okay, okay. Sounds good, sounds good.
Oh, good, right? Easy, right? Okay,
Yeah.
good. So from there, we basically know that this means that this function 5n squared minus 100n plus 10 to the power of 6 is in O of n squared. I almost concluded O of n and I lost it. Okay. Uh so we
Okay.
have that, right? And then the other thing is to show that it's in omega. Okay, so let's go, right? So 5n squared minus 100n plus 10 to the power of 6. Okay, this one is a bit trickier, I would say, but not too difficult. So I would say this is probably greater than or equals to oh, for now we actually do need the n. So I would say this is okay. This is greater than or equals to 5n squared minus 100n unconditionally, right? Um, but I think now I want to do it this way. So I'm going to say that I'm going to rearrange this. So this is basically 4n squared plus n squared minus 100n. Okay, and then I'm going to pull the n out. So this becomes 4n squared plus n times n minus 100. Okay, which I would say is greater than 4n squared when n is greater than 100. Actually, greater than or equals to 100, right? So this should probably work. Because the moment n is greater than or equals to 100, then the right term is positive. So if it's positive, right? So when n is greater than or equals to 100, this thing here is positive, then we're in good shape, right? So then we can dump this term and say it's greater than or equals to 4n squared, right? So now, right, we can say that there exists a constant. The constant happens to be 4, right? So exists a c in r plus, right? C here being equals to 4. There exists a starting point, which actually in n, which actually happens to be equals to 100, right? Such that for all n greater than n0, we have that gn, which is this thing, which I'm super lazy to write, so I'm just gonna control C, control V. So control C, control V, right? Is actually, oops, running out of space. Is actually greater than or equals to sorry, cn squared, pretty much. Ta-da! Right? So it's in omega of fn. So because of that, we can now argue that gn is in theta of n squared, pretty much. Right? So those are, to round up, those are your three definitions: big O, big omega, and big theta. Cha-chang!
Is it necessary that they learn how to calculate the C and the N0?
Uh I think I would just be happy if they could give it, but I guess being able to give the correct one would mean that they need to be able to calculate it. But what
Mm-hmm.
did you mean by that? As in, like, do they need to prove it?
Like actually find the values of C and N0, because it
Yeah,
requires a lot of like mathematical gymnastics, I would say.
it does, but it's high school gymnastics, right? It's
Okay, sure.
university gymnastics, right? Right?
Yeah, they just need some time to think about like how to reason. Because you have a lot of things to play with, right? You can play with the constant and you can play with the
If
n
any,
naught
all
sub.
the more, it makes it all the more easier. Just do it.
Yeah. Okay.
Yeah. Yeah. So yeah, just find the constants. You don't have to like give a formal proof anymore. Like from this week onwards, no more formal proofs required. But yeah, we're back to high school gymnastics. So that's what this is. Yeah. Yes, they should be able to find the constants. Yes.
Okay, okay.
Yes. Okay, let's stop this one and move on to the next recording.
Yeah.